I'm Jeremy Brown. I'm at Louisiana State, and the work I'm going to be talking about today is a collaborative effort with Bob Thompson at the University of Hawaii. So I think it's probably unnecessary to say this in this room, but Bayesian inference has become quite popular for phylogenetics. And one of the main features of Bayesian inference is the need to, or the ability to integrate out uncertainty in model parameter values when trying to assess support for different trees. So if we're interested in the posterior probability of two trees, say tree 1 and tree 2, we can think about all of the possible, say, branch lengths and model parameter values that would be reasonable under those trees and assess their total probability, those total marginal probabilities. Now, unfortunately, in phylogenetics, we generally don't have analytical ways to calculate those marginal probabilities, and so we have to use some sort of numerical method to estimate them. Now, by far the most commonly used method in phylogenetics is, of course, Markov chain Monte Carlo, or MCMC. And the general idea behind MCMC is to start somewhere in tree and parameter space, to propose some new solution, to evaluate the quality of the new proposed solution relative to where you currently are, and then based on those ratios, to accept that new state or stay where you are. And we record those states as we go through time. And so I just want to highlight the role that this acceptance probability that we abbreviate R plays in this process. So if our proposed state is better than our current state, we always move there. If it's worse than our current state, we move there with the probability R. And we do this sufficiently many times, we should hopefully get a reasonably good estimate of what that posterior distribution looks like overall. However, it's well known that MCMC has trouble when distributions are rugged. So if we have multiple regions of high posterior density that are separated by deep valleys, the probability of a chain moving down the valley and up the other peak is quite low. And so chains can become trapped on individual peaks. And so when they become trapped, what we end up with are estimates that are highly biased representations of the posterior. So we tend to sample only one peak or only the other, but not both. So the work I'm going to talk about today was really sort of an accidental project. So Bob and I were doing another project. We were interested in estimating Bayes factors that support a particular bipartition. And in order to estimate the Bayes factors, we had to estimate a marginal likelihood where we integrate across all trees that contain a given branch. We also had to estimate a marginal likelihood across all trees that do not contain a given branch. So we call all the trees with that branch a positive constraint. And the sample of trees that do not have that branch, we say satisfy that negative constraint. And when we tried to do sampling under the negative constraint, we ended up with a very rugged looking distribution. So if we take the collection of trees that we sampled, so this is a tree that has 10 taxa in it, they're widely distributed amniote taxa, and we imposed a negative constraint on the monophyly of birds. And so when we did that, we ended up sampling trees that fell in these sort of three distinct clusters in tree space. So here, each of these points represents a sample from the posterior distribution, and we're just plotting tree space in 2 dimensions. Now, if we look at the trees that represent the sampled points in each of these clusters, we see that each of them corresponds to a different way of breaking up bird monophyly. So we're either inserting a turtle in the middle of birds, tuatara in the middle of birds, or human in the middle of birds. And the reason that this distribution becomes very rugged is because the data really don't want to let birds move very far apart in the tree. They really strongly support bird monophyly. But because we're imposing this constraint, we have to stick something in between birds. But it's actually very difficult to move between these alternative insertions. Essentially, we have to simultaneously, in a single move, remove one inserted taxon and put another one in its place in order to continue satisfying the negative constraint. And so this is what imposes this very rugged landscape on these negative constraints. Now, I felt the need to name this problem. Well, coming from LSU, I decided to come up with the most Louisiana analogy I could possibly think of. And so I'm going to dub this the po' boy problem. So if you imagine a very hungry person who's just been given a shrimp po' boy and they're holding it tightly in their hands, they're about ready to eat it. And at the last minute, for some reason, the chef decides to switch out the shrimp for oysters. The person won't let go of the po' boy. So you have to have a way of changing what's actually in the sandwich while that person is still clutching it. And so The two halves of the French roll sort of represent your monophyletic taxa. The data really don't want to let them apart, but you have to change what's in the middle. And of course, this is a very challenging thing to do. Now, one of the common strategies for getting around these very rugged surfaces is to use a thing called Metropolis coupling. So instead of running a single Markov chain, we run several, and we heat some of those chains. And by heating, I mean that the heated chains sample a flattened version of the posterior. So the valleys become more shallow in these heated versions, and so that chain can traverse the valleys more easily and move between peaks. And we periodically propose swaps between our cold chain and our hot chain. So the hot chain can end up acting as a scout, finding regions of high posterior density for the cold chain. So Bob and I decided to try using Metropolis coupling to get around this sort of rugged distribution we have with our negative constraint. But we started to get some results that we didn't really understand. So we would run multiple runs. This is just one example of the results we got. We run multiple runs. Each of those runs independently sampled all of these peaks in tree space. So they each independently found all of the different ways to break up bird monophyly. And they sampled actually very similar likelihoods. But the posterior estimates between these two runs were actually quite divergent. So if we look at the estimated posterior for humans breaking up birds, it was 0.5 in one run and 0.25 in the other. And these aren't just stochastic differences. You can let these runs go for a very long time, and they'll get very precise and very different estimates of these probabilities. So we decided to try and understand what was going on here. And so we started looking back at the theory behind Metropolis coupling. And in particular, we started paying attention to the acceptance ratio, so this R ratio we talked about at the beginning. And so the R ratio for Metropolis coupling has this form, and really we can break it down into these two sort of intuitive components. So this is the chain-specific density for chain I, and the chain-specific density for chain J. And essentially what this ratio is asking is, does chain I like where chain J is? And then we ask the reverse question, does chain J like where chain I is? And if they're both reasonably good, then we can propose that swap, or we can accept that swap. So that's the sort of most intuitive way to understand that acceptance ratio, but you can also transform it. So here, this is the same ratio, we just transformed it in terms of the actual posterior densities. So we have the posterior density between chain J and the positions of chain J and chain I, and we raise it to this power, which is a function of the difference in the temperatures between those chains. And this has this somewhat strange property of always accepting moves when the temperatures of our two chains are equal. So we're raising it, we end up raising this to the 0th power, and our acceptance probability is always 1. As the difference in temperatures goes up, we start to accept it less often, but still much more often than we would expect based on the actual posterior densities of the two positions of the chains. So we decided to try and explore the ramifications of this in terms of a very simple problem. So we constructed this toy distribution. And so we made one peak very broad but very short. So this has a total posterior probability of 0.2, but it's very wide. It ranges from 0 to 0.8. We have this narrow peak over here that only ranges from about 0.81 to 1, but it's much taller, and so its total probability is 0.8. And then we have this tiny valley in between, but we set up our proposals so that they couldn't jump the valley in just a single move. And then we tried to recover this distribution using a variety of different Metropolis coupling scenarios. So we evaluated different numbers of chains and different maximum temperatures. So the maximum temperature determines how heated our most heated chain is. So which chain has the best ability to cross this valley? And we got some interesting results. So most interesting, when the maximum temperature is very low, so when it's at 0 or close to 0, all of the runs grossly overestimated the probability of the first peak, regardless of the number of chains we used. As we increased the maximum temperature across all these runs, they started to come closer to this true probability of 0.2 here. They never quite got there, though, interestingly. But the maximum temperature played a much bigger role in improving the estimates of probabilities than did the number of chains we were using. And so we can get some sort of intuitive sense for why we're starting out at an estimated probability of 0.8 if we think about the probability of getting trapped on either of these peaks. And so I've sort of done this the capture probability. And so essentially if we start a chain anywhere in this part of parameter space, it will most likely become stuck on peak 1, but if we start over here, it will become stuck on peak 2. So the capture probability for peak 1 is 0.8, and the capture probability for peak 2 is 0.2, despite the fact that their actual probabilities are reversed. So when two runs end up with the same distribution of poorly mixing chains across peaks, they're going to estimate nearly identical but incorrect probabilities. Effectively, they're estimating not the probability of the peak, but the probability that a chain becomes trapped on that peak. So the probabilities are proportional to the number of chains on each peak. Another interesting thing that happens, so here we showed that the number of chains doesn't matter much in terms of the average estimated probability of peak 1, but down here I've plotted the standard deviation in these estimates across runs with different numbers of chains. And counterintuitively, as we increase the number of chains, the standard deviation in these estimates goes down. So what this essentially implies is that as we increase the number of chains, it starts to look more and more like we're getting really good convergence across independent runs. And the reason for that is essentially the law of large numbers. As we increase the number of chains we're running, the proportion of chains that fall on peak 1 ends up closer and closer to 0.8, and the proportion of chains that end up on peak 2 ends up closer and closer to 0.2. So if we ran sufficiently many chains, we could get very precise but still very incorrect estimates across independent runs. So we did essentially the same thing that we did with our toy example, but we did it with the empirical example, so we went back to our negative constraint. And so if we look at the estimated probability for breaking up bird monophyly by inserting humans, we see the same pattern where as we increase the maximum temperature, we start to change and then we start to plateau at around 0.7. But all of the runs essentially estimate the same probability for this arrangement regardless of the number of chains we use. So again, the temperature seems to be much more important than the number of chains we're running. And we saw exactly the same pattern that we saw in our toy example in terms of the number of chains. So as we increase the number of chains, we start to decrease the standard deviation across independent runs. Independent runs start to look more and more similar. So just a couple of warnings. So Metropolis coupling can certainly be helpful for improving mixing in many cases, but it doesn't sort of obviate us from the need to think carefully about how we construct these chains and what they're actually doing. And so we still need to think carefully about how we set up our analyses, even when our chains find many peaks in the parameter space. With small numbers of chains and small numbers of runs, these estimated probabilities can be incorrect, but essentially identical. So if we have the same number of chains that end up on different peaks. And then with large numbers of chains, these will become increasingly similar across all runs. So in the small case, we expect identical probabilities only when we end up with the same distribution of chains across peaks. But in this case, essentially all runs return very similar estimates. I also want to point out too that we've primarily been investigating this idea of a rugged distribution. So we have multiple peaks separated by some deep valley. Metropolis coupling could also be useful for improving mixing on a distribution that was actually quite broad. So if the individual proposals we're using within each of our chains are much smaller than the breadth of the peak as a whole, we might end up with a very different behavior than we get with these rugged distributions. And so I think the way we set up Metropolis coupling needs to be problem specific. So to the extent that we expect rugged distributions, we should pay attention to the maximum temperature of our chains. But if we have broad distributions, we might want to think more about the chain number. So yeah, just some brief recommendations. Using more than 2 runs is definitely helpful to avoid this sort of spurious convergence. For rugged distributions, increasing chain temperature rather than chain number is helpful. And for broad distributions, increasing chain number rather than temperature might be the better way to go. Thank you very much.
Quick comment. Most of the software that does Metropolis couple doesn't do this, but if you take your cold chain and separate